Hey, welcome to episode 5 of the Lockdown DIY series. So today we're going to be going over electrical. Now, so far all the videos I've done as part of this series, hoping to try and help any of you homeowners who are looking to learn how to do some DIY projects around the house more on your own, have been really pretty straightforward. A lot of you probably already knew a lot of that stuff or aren't going to be too intimidated to give it a try on your own. Electrical, though, is a whole other story. If you don't know what you're doing when it comes to electrical work, it could potentially be fatal, and you could easily get shocked if you don't take proper precautions. So I'm going to give the disclaimer right off the bat. If you don't feel completely comfortable doing this work on your own, make sure that you hire a licensed electrician, no matter how small the job, okay? That's very important because this work can be really dangerous. Now, a contractor friend of mine, I remember years back, he told me, the nice thing about electrical is if you mess up, it usually lets you know, right? That's not always the case, but most of the time you're going to know if there is a mistake. You're going to have some sparking, arcing, you'll see some smoke. A lot of different things can happen if everything isn't exactly as it should be. But really, even though electrical is really complicated, and electricians are really smart guys who have to learn a lot of information, HVAC techs have to know about electrical, plumbing, all kinds of things. I always say that HVAC techs and electricians are kind of the brightest guys in the construction industry. Okay, and there's a reason that electricians charge quite a bit a lot of the time and make good money, because this isn't a real simple job and you do have to really know what you're doing to do it right. The things we're going to be going over today, though, are pretty simple things that you can easily do yourself as a homeowner as long as you take proper safety precautions. Now, before I get into that, I want to tell you a little bit about the basics of how electricity works, how it's formed at a power plant, how it gets to your home, and all the different terms that you would commonly hear. Bear with me because a lot of this stuff may sound boring or too scientific, and you might be thinking, well, I just wanted to watch this video to learn how to do some basic stuff. That's fine, but this is really fascinating information. And like anything, the more you know about the topic, the better off you're going to be able to diagnose what's going on and make sense of it, okay? So understanding exactly how electricity works in your home is step number one, really, to really being good with how to do electrical work. So electricity is formed at the power plant by huge generators. And the fuel that's used to make that, to power those generators, is usually fossil fuels. Things like coal. We can have renewable sources like wind. You could have natural gas. But around here, it's mostly coal. And these giant generators spin, and they spin at different points along a circular path, and they create different poles. So that causes the current to move in alternating directions. And that's why in residential homes, we have what's called alternating current as opposed to direct current. So that's AC power versus DC power. So we're not talking about the band, good band, but we're talking about AC versus DC power. And back years ago when Thomas Edison was discovering things about electricity and Tesla was, there was a big debate throughout the country about which one of the two, DC or AC power, was going to be used in homes, and AC power kind of won the battle. So we'll talk a little bit more soon about what makes the two different, but just remember alternating current and direct current. So once the electricity is generated in the power plant, it's at very high voltage and it gets sent through a station near the plant where it then gets increased in voltage so it can travel through transmission lines. These are all throughout the country. They're the big metal towers you see with big lines running across them, usually on hillsides. And then they get to a step-down substation, another transformer, where the energy is converted down yet further, and then to another transformer out at the street. So this is either going to be a smaller transformer up on a pole on your street, or it's going to be in a pad mount, one of the green box stations down on the ground. And then from there, the power is converted further down so that the voltage is at a point where it's safe to be used in a residential home, which typically is 100 amps or 200 amps. And nowadays, 200 is what's most common. Older homes will likely still have a 100 amp service if they haven't been upgraded. But we don't really want any more than that, generally speaking, for a residential home because we don't want to overload anything. So the voltage that is carried on those transmission lines is much higher on those lines than when it gets to our home. Now, when the electricity gets to the transformer and it's converted down, it then travels usually through 2 wires, and this is all on one phase for homes. So this is called single phase, and more technically it's split single phase because that one phase of power is split into 2 wires. They each carry 120 volts, and combined we have 240, and in the center of those we have a neutral wire, and we'll talk a little bit more about this in a second. So from there, power travels either overhead or underground to the electric meter that's outside your home, and from there it travels into your main panel inside the house. Those 2 legs, and they're usually black wire and oftentimes aluminum, stranded. So we can have solid wire or stranded, and their names are a dead giveaway of exactly what they look like. It's either one thick piece of wire or several strands that are clumped together. Usually we have stranded aluminum wire as our hot legs that are each feeding 120 volts into each side of your panel. So from there, it goes out through all of your circuit breakers or your fuses and through what are called branch circuit wires, usually copper, and that's called non-metallic sheathed or NM copper wire. And each one of those wires directly corresponds to the breaker size. Now remember this, all wire ratings are typically given in what's called AWG, which just stands for American Wire Gauge. That's been used since the 1850s, that designation, so a long time. And this is true of wires and a lot of other things, but when it comes to gauges, the smaller the number, the larger the size, okay? Remember that. So a 15 amp breaker that does not supply as much power as a 20 amp breaker is going to carry a higher number wire gauge. So a number 14 copper wire corresponds with a 15 amp breaker. A number 12 wire, a lower number, corresponds with a 20 amp breaker, and a number 10 with a 30 amp, and so on. So you can see the lower our gauge number, the higher the higher the breaker number that it corresponds to, and the more current can be carried along that line. So when we get to our terms, voltage is measured in volts, and voltage is the pushing force behind electrons, and that's really what electricity is. That's where it gets its name. It's the movement of electrons, and it's a lot of electrons over a really quick period of time. So we call the measurement of those coulombs, and a coulomb is, I think, 6.24 times 10 to the 18th power, which is like quintillion electrons per second. So 1 amp, and we measure our current, which is like our flow of electricity through a wire. 1 amp is equal to 1 coulomb, all those electrons per second, okay? And it takes 1 volt to pass 1 amp of current through 1 ohm, which is our measurement of resistance, through a point in a wire. So the analogy that you will typically hear for how electricity works, and it's probably about the best one, although it's not perfect by any means, but think about a plumbing system. So your wire is like your pipe, and voltage is like the water pressure. Amperage, measured in amperes or amps, is like the water flow through the pipe, and ohms, or electrical resistance, is similar to the diameter of the pipe, okay? So obviously the thinner the diameter on your pipe, the more resistance there's going to be. So all these things come into play when sizing and installing an electrical system, okay? So one big difference between electricity and water, though, your electrical system and your plumbing system, is that on your plumbing system, your supply, your pressurized water comes in on one side and it drains out another side. So they're separate. With electricity, your current is always trying to return to its source or to return to ground. So it moves in a circular motion, okay? Think about that. So when we have a typical wire like this, and I'm going to cut this open to show you a few things. We have a black wire, which is the hot wire, and we have a neutral wire, which is the white wire. And then we have a bare copper wire, which is the ground. Okay, so you can see our 3 wires here. And this is a number 14 wire. This is called a 14-2 wire. You can see there are 3 wires here, but we've got 2 main wires that are usually going to be dealing anything with our current. So we have our black hot wire, and this is what's supplying electricity to the different fixtures in the home, receptacles, switches, lights, and so forth, from the source, from your panel. The neutral white wire then has a 0 potential, but it's carrying current back to the panel and then back to the transformer out at the street. The ground wire is normally never going to be carrying any current, period, unless there's a fault. And just like its name suggests, the ground is meant to go directly to the ground. So we have electrodes or grounding rods that go down into the earth, into the ground, literally, so that if you have like a lightning strike or if you have a fault in the system, that stray current can travel safely along this bare copper wire, which has very low resistance, so that you don't get shocked. Instead, the current will just travel back to the earth and eventually then back into the grid again. So hopefully all this so far is making sense. I know it's very complicated, but it's also very fascinating how all of this works. And again, understanding how these things work will really help you to know more about how your electrical system works so you can diagnose things a little more easily. So we're going to move on now to the next portion of the video where we're going to get a little more hands-on with tools and how to do some things yourself. Okay, so some of the most common tools that you're going to be using for electrical work on a DIY basis, I have right here in front of me. Now, first of all, as an inspector, this is one of the tools I use more than anything. This is a simple outlet tester. You can see here that there is coding on here. Now, after you use these a while, you just memorize what they are, and most of them are the same, but they all have a code. These run about 10 bucks or so. You can get them at any hardware store. But all we do is we plug this into a typical 3-prong outlet, like what we have here, and this isn't powered now. But once we do that, this is going to light up if there's power at all to the outlet, and it's going to tell us with the code of our lights what we have going on. So on my tester and on most, the middle and the right lights being lit up means that we're properly wired and grounded, so we're good. If we have the middle and the left side lights lit up, that means we have what's called reversed polarity. We'll talk about that more soon. If just the middle light is lit up, see this a lot, it means that the outlet is powered, but it's not grounded. We see this a lot of times in older homes where maybe there's knob and tube wiring that doesn't have a grounding conductor, and outlets were just swapped out, older 2 prongs with 3 prongs, and the electrician or the homeowner didn't do anything about grounding them. So that's very common. So if you want to check the status of your outlets to make sure that they're properly wired, you can pick one of these up and you just plug them into the outlet and read the code here, and it's as simple as that. One quick tip, make sure, this kind of goes without saying, but normally in most cases, our grounding hole on the receptacle is facing down. If it's facing upside down like this, which is arguably preferred, you're going to have to turn the tester upside down to plug it in this way. And if you do that, then obviously everything here is now reversed. So it would be your middle and your left lights being on that would be correct, whereas normally it's the middle and the right. So I trust that you understand how that works. That's not too difficult. Okay, so we have wire strippers. You can see here on this tool, it gives us our American wire gauge and then a corresponding number. So we've got 14, 12, 10. And all this means is that the hole you see here right next to that number is just enough to put over top of one of our wires of the corresponding gauge to strip off just that sheathing and not damage our wire. Okay, so this is how that works. And typically we're going to be cutting off about a 1/2 inch or so if we're going into like anything we're connecting to with one of these wires. So I'm going to get it to about where I need it. This is a 14 gauge wire, so I'm putting it right in the 14 slot, and you just squeeze down and pull off. So I have removed the sheathing without damaging that wire at all. I'm going to do the same thing here real quick on my hot side. And they make all kinds of different strippers that you can use. So that's how easy it is though. Okay, so now we've got good wires ready to go. We also have wire cutters. Look like this. Needle nose pliers. So these have long, thin noses. And then we have, these are special pliers that you often see electricians using. And one thing that these are really handy for is twisting our wires together. So whenever we're going to be connecting wires in a wire nut, we need to be able to twist them together. Now we're going to talk about how to join wires together with a wire nut. We have different color wire nuts that are indicated for connecting different size wires. I have a couple here that I just had laying around as examples, and these are pretty common. So this orange one, which is pretty small, you'll typically see this used for connections at like fans, smaller fixtures, switches, things like that. This yellow nut, a little more common and it's a little bigger. This is commonly used to join two number 14 wires, which will be connected to a 15 amp breaker, or two number 12 wires that will be connected to a 20 amp breaker. Okay, and those are your two most common breaker sizes that you'll see in your panel, 15 and 20 amp. Okay, so I'm going to go ahead and cut off another section of black wire here just to show you exactly how this works. And I'm going to have to strip this other one first. So we're always going to be connecting black to black, so hot to hot, or white to white, neutral to neutral, or bare copper to bare copper, which is ground to ground. Now, the pliers here are great for making this connection. So we're going to just put our wires together like this, and we're going to pinch these at the end, and we're going to use the tool to just turn them in place. This is a lot easier than doing it with only your fingers. Okay, so we're going to do this several times until we get it wound around really nicely. After we get that done, I like to take the wire cutters and just snip off a little bit at the end here. And then we're going to take our wire nut around the end and we're going to turn this in place. Okay? Very important that you use a wire nut for this and not electrical tape over that. Now, some people will argue that once you've got the nut in place, wrapping tape around the bottom of the nut is a good idea. Some people will argue that it's not. It's interesting, in the world of electricians, there's actually still a lot of debate on what the best practices are. But this is all that's required to make these connections. I personally tend to err on the safer side. I do like to tape up any joints that I can. When I'm done wiring an outlet, I like to wrap tape a couple times around our screws, and we're going to go over that now. Okay, so let's say here, and I'm going to go ahead and cut this wire again and get these ready to go. All right. So to cut the wire itself, if you don't have anything already exposed, and normally out of an outlet box, we want about 6 inches of wire to work with. A good gauge for that is with most utility knives, you can just go up from the bottom of the wire, and then to that point, you're going to cut right down through the middle, and that'll be between your black hot and your white neutral wires, so you shouldn't cause any damage. Then you're just going to pull back the wire sheathing here. So now you can see we've got our black hot, our white neutral, and our bare copper ground wires all exposed. Okay, so I'm going to take about 1/2 inch in the 14 gauge slot off each end, and I'm going to connect these to the outlet just to show you how this works. Okay, so on our outlet, we have our hot side, which has the shorter slot. And this is the supply side where the power is entering in to the outlet. And then we have 2 brass screws on our hot side. Okay, so anytime you see the short, think hot, or the brass screws, think hot. On the other side, the longer neutral slot, we have 2 silver colored screws, and we also have our green ground screw. So in general with electric, always think green and ground, GG, okay? Now the ground is on this side of the outlet because we want to keep it as far away from the power source as we can. By the way, one other quick thing, earlier I discussed volts, amps, and ohms, resistance. What I didn't mention yet was watts, which is a measure of wattage. So wattage is a measure of our power, and typically you'll hear things referred to in terms of watts. Okay, like your microwave, for example, is going to be rated for a certain number of watts. Watts, we get that by simply multiplying our volts times our amps, and that's going to give us the total wattage for that circuit. Okay, so one other little quick thing about the anatomy of an outlet. So over here, we've got a little piece of metal that's connecting the screws, and we have it on each side. And then you can see here, there's a little tab that connects these. Those tabs can be removed so that you can actually isolate or separate these receptacles from each other, so that one could be continually powered or live all the time, and the other could be, say, switch controlled. In that case, they would need to be on separate circuits, and you would really need to know that before you wire the house. Okay, so if you want to make that alteration, that's really a job for an electrician. It's not a DIY task. This video is really just to help you with what's already existing in the home. So just remember, those jumpers are there to create continuity between the screws, so that we only have to have one wire on each side to complete our circuit. So in order to wire this, now most newer outlets come with these slots in the back that you can just stick your wire straight into, okay? But there's a little release on here, and sometimes after these have been sitting a little while, it's difficult to get these out very easily. I still personally prefer to go the old-fashioned route of creating a J-loop at the end of your wire here to wrap around the screw, and then nice and firmly tighten down your screw. So in this case, we have our black wire that needs to go to our brass screw on the hot side, and then our neutral wire that needs to go to the silver screw on the other. So what we're going to do is just take our needle nose pliers here. We're going to pinch this at the end and just fold over, okay, to create that little hook. We're going to do the same thing here for the neutral side. Now when we connect these, it's very important that we connect them along the same route that our screwdriver is going to be turning. So I'm going to be turning the screw in clockwise. I want to be sure to install this around the screw clockwise as well. okay? So once I get this on here, I can now screw this in, and I'm going to recommend do not use a screwdriver, a drill, a power drill for this. Use a screwdriver by hand to hand tighten these down nice and snug, okay? And then on our opposite side, we're going to do the same thing, again making sure to have our hook in the same direction that we're going to be turning our screw. So I've got that on there. And then we would also attach our bare copper ground wire to the green screw on this same side. Now, if you test an outlet with an outlet tester and you get a reverse polarity reading, all that usually means is that if you were to pull the outlet out from the wall, you would see that it's just been wired backwards, that the black wire is on a silver screw on the neutral side and that the white neutral wire's on a brass screw on the hot side. All you need to do is make sure the power is killed to the outlet and that everyone in the house knows you're doing electrical work and they can't turn anything on, and you're just going to simply untighten these screws, swap your wires, and tighten them back down. That's all it takes to fix a reversed polarity outlet. Something we run across all the time. It's such a simple fix to do yourself, okay? So that's all that you have to do, and that's the anatomy of an outlet. Hopefully this has been helpful. One of many things that you can do on the electrical side as a DIY homeowner, and one of the simpler. Okay, so next we're going to be talking about how to test an outlet with an outlet tester and how to check its voltage, make sure that it's getting ample power with our multimeter. All right, so next tool in the lineup. This is what's called a multimeter. Turn it on here real quick, and you can see here these symbols. This little squiggly line, that refers to alternating current. The V's for volts. And the little line with several dotted lines below it is direct current. In a home, we're dealing with AC, with alternating current. So you're going to want to turn this to there, okay? And a lot of these come with a backlight too, so that it shines bright and you can see this more easily. But this allows us to see how many volts we have and if the number is proper. Okay, so we're down here at an outlet now. We're going to test it. First, we're going to use our outlet tester to make sure that we're properly wired and grounded. As long as our middle and right sides on this tester light up, we know that both are true. So we're good. Now I'm also going to test the bottom receptacle just to make sure that it's not on a separate switch, that we're on the same circuit and it's also powered. So again, we're good. Now this tester tells me then that this outlet is properly wired and it's grounded, but it doesn't tell me anything about the specific voltage running to it, okay? So for that, I'm going to use the multimeter. And we're going to turn this to the V with the squiggly line, that symbol. That means we're checking voltage in an alternating current system. And this multimeter, it's called multi because there are multiple things you can test with this. But for typical around the house DIY stuff, this is pretty much the setting you're probably always going to be on. Okay, so to test the voltage in the outlet, I'm going to check from my hot side, the shorter slot, to the neutral. And we should get about 120. Okay, you can see here we're reading 122.6. So we're good. Now, if I move to my neutral and ground, both of these, as we talked about earlier, they should have 0 potential. So I'm reading at under 1 here, okay? So that tells us that everything with this outlet is exactly as it should be, and we're good. So that's how to use an outlet tester and a multimeter. This is a more expensive tool, but it can really come in handy when you need it. Hey, I mentioned earlier in the video that I would go a little more in depth about DC or direct current versus AC, alternating current, which is what our houses are powered with. So in direct current, just like it sounds, our current is always traveling along one path, whereas with alternating current, it's alternating back and forth along the line. So one thing that's really neat about that is with alternating current, the current is actually moving as a wave, and that's measured as a frequency, which in the US is 60 hertz. What that means is that 60 times every second, our light bulbs are flickering on and off, but we can't tell because that's way too fast for the human eye to be able to detect. So I thought that was just something that you might be interested to know, one of those really cool facts that most people are unaware of. All right, so hopefully this video has been helpful. Hopefully it's helped you to learn more about the way electricity actually works, which is really fascinating, how it powers the things that we often take for granted every day in our home that we feel like we really couldn't live without. And has given you some pointers on how to do some testing of your own, of the outlets in your home at least, and how to make some simple repairs. Please feel free to like, comment, share. We're trying to get these videos out to as many people as possible during this lockdown time when we hopefully have time to get more done than we usually would. Thanks for watching.